Hello, everyone. Nice to see you. Hi. Hello. Good afternoon. How are you doing, guys? Okay. So, but yeah, hello, everyone who just joined. And I guess maybe more people will join a bit later. So, just short recall of our previous discussion. So we introduced uh, three laws of motion that was, let me maybe write it down again so we have it. Okay, first law of motion. We had that in the inertial system of coordinates, or like inertial frame of reference, if the net force acting on the body is equal to zero, then its velocity doesn't change in direction, so it moves on a straight line, and it is either equal constant or it is zero. So the body doesn't move. So such a case when the net force acting on the body is equal to zero stands for the case of a quasi-free body. If body is free, then there is no any forces which act on this body. So of course that's also definition of the first law of motion when we explain this on based on the free body. So second one is acceleration is a result of acting some force on a body with some mass m, and this mass should be underlined as inertial mass, and we discussed the difference between inertial and gravitational mass. And the third one that we have is if we have some acting force in the system of two bodies, for instance, and we obviously should have always reacting force, which will be equal in magnitude, but different, like opposite in direction. So this is what we discussed in details last time, and today we should continue with considering different applications of Newton's law. So with this, let us consider, for instance, let's start from inclined plane. So we have some inclined plane with the angle theta. And we have some body on it. Obviously, here will be some force mg, which is the weight of the body. It is convenient to use a system of coordinates where axis y is perpendicular to the surface of the inclined plane, and axis x, which is going along the surface of the inclined plane. So we can now consider what other forces will be and how they will be aligned with respect to each other, with respect to the surface. So we definitely have some reaction of the surface and we can split our weight of the body in two components. So it will be one component along axis y. Let's show it here. And one along axis x. So this one along axis y, we will determine based on the orientation of the weight vector with respect to the normal to the inclined plane surface. And that will be angle theta, the same as the angle between inclined plane and the horizon. So now if we have this angle theta, we can write that this component of our weight will be along axis y. So it will be mg times cosine theta. Guys, please switch off your microphones when you don't ask questions. And another component along axis x here will be mg times sinus theta. So obviously then n reaction of the surface should be equal to the y component of the weight. And there is some force acting downwards along the inclined plane, which accelerates the body. So in total, let us write for both like projections of all forces on each of our axes, x and y. So for y, we will get n, which is positive because it's along axis y, minus mg times cosinus theta, and this is equal to 0 because they compensate each other. So this body will not move along axis y for sure. Then axis x will be what is positive here, and this actually is the only component which we have so far. This is mg times sinus theta, and that will be equal to m times a. Sorry, where a is the acceleration. So if we so far don't have any friction, imagine it's like very smooth surface, no friction. We will discuss friction a bit later in more details. Then we can actually calculate a from the second equation for x. It will be a is equal to g times sinus theta. And because we just cancel this mass here. And from here, what is, it has some practical interest, because from here we can express g as a divided by sinus theta. So this is a good way to measure accurately acceleration of free fall, because if we have falling just downwards, this happens quite fast and it's difficult to measure such high acceleration. However, if we use an inclined plane with like negligible friction between the body and the plane, then we can use quite small angle theta. So this acceleration A will be very small. We can measure it easily and accurately. And then by knowing this small acceleration and angle theta, we can accurately calculate the value for G. Okay, let's go for another example. And this time it will be some lift with a weight, some body inside it. So let's draw a lift. We have some body here with weight mg. So let's put here axis y goes from down to up. And when it is stationary condition, so we have either, so we have constant velocity or zero velocity. So acceleration is equal to 0 of this system. Then there will be another force, which is reaction of the surface where this body resides. This will be n, and it will compensate the weight. So everything is good. However, let's consider what will happen when we have some acceleration in different directions. So now for this particular case, when a is equal to 0, taking into account the orientation of this y-axis, we can write that n, which is positive, goes along one y-axis minus mg, is equal to 0. Okay. So let us consider acceleration a, which is pointed upwards of this lift. Then we get some like motion of this body with some acceleration. So we can write m times a, which is positive because it goes along the axis y, is equal to n minus mg. So from here, we can already calculate this new reaction force, and will be equal to m a plus g. So if we put mg from the right side to the left side and take out from parentheses the mass. So we see that our reaction of the surface increased now because of additional acceleration, which is pointed upwards. So if we have acceleration of the system which is pointed downwards, then we can write for a. So this is for a larger than 0. This is a smaller than 0. We can write minus m times a equals to n minus mg. So now if we do this, the same manipulations, we get expression for the reaction of the bottom of the lift, like surface where this body is located, as m times g minus a. So in this case, it is decreased. And if from this equation we see that if we have a equals to g, then it will be 0. So n is equal to 0 when a is equal to minus g. So in this case, we have free falling condition, and there is no reaction of the surface on which this body reacts on the body. So it actually is in free falling condition, which can be realized quite efficiently with some special airplanes, which are used for training of astronauts when they go up and just rapidly go down with the acceleration of 1g. And it's realized continuously on the International Space Station, which continuously falls down from like on the surface of the Earth. However, it does it, like it moves so fast that it cannot reach the surface, so it stays in this free fall condition continuously. And this is the reason why you don't have any gravity effects on objects and humans which are on the International Space Station. It's not because it's so far in space that gravity doesn't work there. Actually, it would be something like 80% of Earth's gravity on that location, or that height of the International Space Station. However, because it's continuously in this free falling condition, we can observe like zero gravity environment. Okay, so now we can proceed further, and next we will consider in more details different types of friction forces. That's important part of application of Newton's laws, because friction will definitely have a strong impact on the motion of bodies. So for this purpose, let us consider some surface and a body residing on this surface. So which forces will act on this body? First, we have the weight of the body, mg. Then we have reaction of the surface. And now, so this is compensated, nothing is going on. Now imagine that we have some force exerted on this body, F. So since we have some not compensated force, looks like this body should move with acceleration A is equal to F divided by M. However, this is not the case from our everyday experience. Usually that requires certain minimum force to move body from its residing position. And that is happening because of existence of such so-called static friction force. So the static friction force is acting always in opposite direction to the applied external force, F static, and it is defined by by two parameters. So static force is equal to mu s times n. So mu s defines its so-called static friction coefficient, and that defines the properties of two surfaces: surface of the surface conditions where the body is residing, like it's located, and also surface of the bottom surface of the body with which it's in contact with the surface where it is located. So these two surfaces, they define how much they will interact with each other. So you can, for instance, imagine some two glass surfaces which are very smooth, and some wooden surface which maybe not so smooth. Then obviously you will get a higher static friction coefficient for this wooden surface, because there is much more chances of a more developed surface area, and these surfaces can interact better with each other, so providing larger static friction force. So this static friction force will be equal to the applied force until it reaches its maximum value, which is defined by this mu s times n. So it will increase proportionally to F until F is not large enough to overcome this maximum value for static friction force, and that in that case it will start moving. So when it starts moving, so in this condition it should be F like equal or larger than static friction force. We go to another regime of friction between these two surfaces, and that is called kinetic friction. So F kinetic. So when this body starts to move with some velocity, then we have F kinetic acting on this body. And this kinetic friction will be defined as the product of kinetic friction coefficient mu k times n. What is important to underline here, that for both static friction and kinetic friction, we don't have area of the surface, of the contact surface. So it doesn't have an impact on these forces. These forces defined only by reaction of the surface, of the bottom surface, which is equal to the weight of the body in this particular case. And conditions of the two surfaces which are in contact with each other. So that is important to know. Another thing that for different surfaces, we can write that kinetic friction coefficient is smaller always than static friction coefficient. So that automatically means if we, and since we don't change this n, that kinetic friction force will be a bit smaller than the maximum static friction force. And if we show graphically this, it will look as follows. Let's say we have here axis of force, and here is axis of friction force. So it's applied force along horizontal axis, and along vertical is friction force. So at some point, it will go from 0. And if we increase applied force, linearly will increase directly proportional to this applied force will increase friction force. And then it will reach to some maximum, which is our maximum value of static friction force. And this is mu s times n. Then it will go like very rapidly here. It's a moment of starting of the motion of this body will go a little bit down and then saturate. So this saturation will happen at the level defined by kinetic friction force, mu kinetic times n. And as you see that the maximum static friction force will be a little bit higher than the kinetic friction force. So we can define here like two regimes. We have static and kinetic. Okay, so now we need to talk about some drag force. Drag force acts on the bodies which fly in atmosphere or flow in some water. So when we have a bit different, we don't have two sharply defined surfaces which are in contact with each other, but for instance, if a ball is flying in atmosphere, it interacts with atmosphere with all its surface, and there is certain drag force which slows down this ball. So that would be also good to mention in this discussion. So let's say we have some ball and it's moving with some velocity. And here is some interaction with the atmosphere in which this ball is moving. So if here we need to consider some cases. So for low velocities, when velocities are not very high, we can write that the drag force, and this drag force is always oriented in opposite to the velocity vector, which is also the true for kinetic friction force. So it's always oriented in the opposite direction to velocity vector. So this will be equal to minus k times v. So as you see here, we have also some coefficient of proportionality, which will define the surface properties of the ball, and also like viscosity and other characteristics of the environment where it moves, like in this particular case in our atmosphere. But obviously it's easier to move in air and then to move underwater. So it will be much higher density, higher viscosity, and will be a huge impact on the environment on this drag force. So that is taken into account by this coefficient k. And we have here velocity, which is interesting. So we didn't have impact of velocity on the friction between two bodies. So for this kinetic friction condition that was independent on velocity, what was defined only by the properties of the two surfaces which are in contact and the reaction of the surface N. Here we have this dependence on velocity, and that is important because it will increase as the body moves faster. In this case, it will be linear dependence. However, if the speed of this body becomes quite high, then this drag force dependence on velocity becomes more intense, and it goes to another regime where it is like drag force at high speeds can be defined as minus K1, so it will be a bit different coefficient, which is because we have a bit different interaction form of like conditions of interactions between the flying ball and air. So we get some turbulence effects, and that should be taken into account also. And because of that, also we have a stronger dependence of drag force on velocity, and we get velocity in second power. So this means that drag force will increase faster in this high speed regime with velocity as we compare it to the low speed regime. So here I would underline that when we want to deal with some laws of motion applied to this drag force condition, you need to understand that it's a bit more complicated in comparison to other examples, because here we have dependence on velocity. For instance, if we consider some ball moving in this environment, let's say air or water, at some constant velocity v, and then from some moment of time, for instance, we want to understand how it will slow down in the this environment. Here we have this drag force, and obviously if there is no driving force which pushes forward this ball under this drag force, it will slow down. The problem is that this drag force will not be constant, as in the comparison to example of a body on the surface. This kinetic force is constant, it doesn't change with velocity. So while it slows down, it still remains the same. However, here, once the ball slows down, you see it depends on velocity, so the drag force will decrease. And then we need to consider this as like some function of time, because both velocity and drag force will depend on time. So we can write that, for instance, m times a, like acceleration of this, like slowing down the ball or accelerating from zero, when we just provide some velocity to this ball. But it always will be slowing down because of drag force. So because it's opposite to the velocity vector. So we can write that this is mass times first derivative of the velocity over time. And this will be equal to so if we consider slowing down, let's say we initially had some velocity, and it will be minus here because this will be negative derivative dv over dt. Since the body is slowing down, it will be negative. And that is equal to k times v. For instance, we consider this case when we have linear dependence. It's a bit easier. So then we can rearrange a bit this equation. So we can write that minus m divided by k times dv divided by v is equal to dt. So we have this differential equation where we can split it in two parts, left and right. Velocity related components are in the left and time related in the right. So if we now integrate this, we will not do it, so we have some time to consider other examples which are relevant, but you see the concept. So you cannot consider that drag velocity is constant. It doesn't, it changes with velocity, means it changes with time. So you need to deal with a differential equation. It's quite simple in this example. And then you can proceed further with the derivation for velocity as a function of time. And once you have velocity as a function of time, you can substitute it in this equation and get drag force as a function of time. So this is the approach you need to follow. So let us go further. And I probably skip this part with inclined plane with drag force. So I think it's quite obvious example. So we don't need to, it's the same example as we discussed earlier, but then we have additional drag force. But maybe let us do it first, because could be useful. So we have some body, have mg, then we have this x component of mg will be mg times sinus theta. Here is our n, which is equal to mg times cosine theta. And here we will have static friction force, Fs. So now the question is, at which angle theta this body will start to slide down. So that is condition when mg sinus theta is larger or equal to Fs. So from here, and this Fs is equal to mu s times n, and n is mu s times mg times cosinus theta. So now we see we can cancel out this and this mg and get the value of this angle, critical angle. So it will be sinus theta divided by cosinus theta, and this will be equal to tangent theta equal to mu s. So technically, the static friction coefficient will define this, the only parameter which defines this critical angle at which the sliding of this body will start, taking into account the static friction force. By the way, coming back for a second with this drag force, you see that it increases with velocity, and at some point when, let's say, we consider some free falling condition, Here is the body, here is mg, and here is AV squared. So at some point, mg will be compensated by the drag force, and that is happening at so-called terminal velocity. So it will be mg is equal to kv terminal squared. And this terminal velocity is the maximum velocity of falling body in the atmosphere or in any other environment, depends on this coefficient k. So it will be mg divided by k and square root of it. So for a human body, this termination velocity is something for falling in atmosphere, it's something around 200 kilometers. So human cannot, without any additional aerodynamic shapes on it, cannot fall in atmosphere with higher velocity than about 200 kilometers per hour. Okay, so with this we already discussed, and let us consider some example of uniform circular motion. For instance, we have some body attached to a rope. So this rope is massless and not stretchable. The length of the rope is L. Then the weight is mg. It rotates about this axis. And the question is, what will be this angle theta, the deflection of the rope with respect to the axis of rotation? So obviously here we will have few different forces acting on this body. So it will be mg, we already shown it. Then we have T, which is tension in this rope. And we will have also centrifugal force, which will act like this. From our previous discussion, we remember that it's mass times centripetal acceleration. And this is omega squared times r. And r is this distance from the body to the point located on the axis of rotation. So short comment on centripetal and centrifugal forces, so to underline the difference, but technically it's the same. It's like the same, like different sides of the same coin. But you need to understand why it's different. So we have centripetal acceleration, which is pointed toward the center of the curvature of the circle. And there is also centripetal force, which technically keeps the body on this curve circular trajectory. So if we consider an example of somebody attached to a rope, and then we start to rotate this body with the rope, then the centripetal force is a tension force in the rope, which keeps the body on this curvature. However, there is also centrifugal force, which is like apparent force. So it's something, if you sit on some spinning wheel in horizontal direction, then you are rotating fast. So you feel that certain force tries to push you away from the center. And that's apparent force. It's not kind of real force. It's like what object is experiencing when it is part of the rotating system. So it is equal to centripetal force, but is pointed away from the center. And the difference is just only in difference of system of reference systems, like frame of reference. If you consider if you're external observer, so you kind of see this centripetal force which keeps the body on the circular trajectory. However, if you are part of the rotating system, you experience some apparent centrifugal force which pushes this body away from the center. But by magnitude, they are the same, and it's all about the frame of reference. So now we want to know which parameters will define this angle theta. And also we have this given angular velocity, omega, besides other parameters. So we can write that it will stay in stationary condition in terms of angle theta, will not increase or decrease, when the centrifugal force will be equal to the projection of tension force T on the radius. So we can write mg is equal to T times sinus theta. So we can draw actually here this force diagram to be more clear. Mg here we have m omega squared times r. Here we have T. So projection of this T on radius, this is our angle theta, will be T times sinus theta. And also we need to compensate this weight. So it is compensated by another component of our tension, which is mg is equal to T multiplied cosine theta. Or actually, sorry, here is not mg, it is m omega squared times r. So now we have these two equations which define the stationary condition for theta, that it doesn't change because mg is compensated and centrifugal force is compensated. So we can express r, radius of this circular motion trajectory. It will be L, length of the rope, times sinus theta. So when we have this expression for r, we can substitute it here and get m times omega squared L times sinus theta is equal to G like mg divided by cosinus theta. So we can get expression for t from here and substitute it here. Get times sinus theta. And now what we have here, we can cancel m and cancel sinus theta. So we get cosinus theta is equal to G over omega square L. So this is our equation, which tells which parameters define angle theta. So it's acceleration of free fall G. So the larger G, the larger cosinus theta, and the larger cosinus theta means the smaller angle theta. So obviously, if gravitation is stronger at all other given parameters, theta will be smaller. And opposite happens with omega square and L. So, but the most influential parameter is omega, the angular velocity, because it comes to this equation in square, in second power. So it will have the biggest impact. If we increase it, cosinus theta will rapidly decrease, and means that theta will rapidly increase until it reaches, like approaches to 90 degrees when we spin with very high angular velocity. So this is pretty much everything what we managed to discuss. There are obviously many possible applications of laws of motion. So we discussed the most common, and also what is important, introduced the friction and drag forces in this discussion. Also we discussed that the circular uniform circular motion, how it can be analyzed in the scope of second law of motion. This is everything what we had time for. It's already a bit exceeding our time. Thank you very much for attention. If you have any questions, you're welcome, or we can also discuss it during our next meeting on Monday. But keep in mind that these applications of laws of motion are very common in problems, so you please go through them and practice with solving problems, because definitely you will be requested to solve similar problems based on these three laws of motion and their applications.
Okay.
Okay, thank you for your attention, guys. Have a good weekend.
Okay.
Take care.
Thank you. Goodbye.
Bye-bye.
Thank you. Bye.
Bye.
Goodbye. Thank you.
Bye.